This presentation is brought to you by Joshua Winsel, Andy Ivy, and Jesus de la Cruz. In general, a siphon is an apparatus that forces a fluid to flow above its reservoir height, to then be discharged at a lower elevation by utilizing atmospheric pressure differences. An experiment was conducted in order to validate a possible math model that predicts the flow rate of a siphon. Testing included various lengths and diameters of tubing, as well as several reservoir height differences. Concluding from the results, a math model built from the modified Bernoulli equation is able to predict the flow rate of a siphon within plus or minus 10% error.
For our literature review, we refer back to the Fluid Mechanics and Fluid Thermal System book. In the project, we made the following assumptions. We used a large reservoir. We said it's an incompressible flow. We said it has a constant cross-sectional area throughout the pipe. And we said it's an isothermal flow. We decided to use the energy equation because it involves both mechanical energy and thermal or work energy, whereas the Bernoulli equation only applies mechanical energy. We can cancel out the pump, turbine, and pressure heads as well as the velocity at the top of the reservoir and end up with this small equation. The minor loss can be found from tables of books and internet sources, but from this equation we still have to find the outlet velocity and the friction factor. So we have to iterate using the Reynolds equation and the friction factor equation for a laminar flow first, and then if the Reynolds number is greater than 2100, we use the Churchill equation because we will be dealing with turbulent flow. And finally, we can use the flow rate equation to predict the flow rates at each test.
To conduct our experiment, our experimental apparatus consisted of a wide mouth reservoir, a holding block, a holding clamp, graduated beaker, and adhesive. The flow rate was measured by careful observation using a stopwatch to check time intervals between fluid levels. Experimental results were then added to an Excel file where they were compared with the math model results. To validate our experimental results against the math models, we ran multiple trials with each scenario. We varied tube length, varied tube outlet height, and used variable tube inner diameter and materials. All in all, tubes with 3 different materials, 3 different diameters, 3 different heights, and 3 different lengths were tested.
Through our experimentation, we learned that testing all input parameters is fundamental to understanding all the output parameters. For example, adding length to the siphon decreases the flow rate. The friction factor of a material has little effect on the flow rate compared to other factors. Varying the siphon diameter produces the most significant changes in flow rate. From the experimental data, we determined that our math model predicts flow rate within plus or minus 10% error. Even with eliminating head losses by using a wide reservoir, there are other factors adding to the error of the math model. Even at this rate of error, the model predicts well enough for most practical uses.